Hello, everybody. My presentation today is uncoded caching for future improved networking. I'm going to provide an introduction to coded caching, then some of its application and some of challenges that are associated with its implementation. Okay. Trying to first. Oh, okay. First, let's go through some introduction. What's coded caching? In order to introduce coded caching, I'm using a very simple classic example. Consider a network of two users which are connected through a shared link to a single server, and we have two files A and B. And each user is equipped with a cache memory of size 1 and might request one of these two files. And we don't have any information about the request probability distribution. The question is what to put inside the cache memory of each user so that the load on the shared link is minimized. This can be a wireless or wired scenario, but in this presentation, I'm going to assume wireless communication mostly. One solution is to put randomly files inside the cache memories. For example, put file A into cache memory of user 1 and file B into the cache memory of user B. File B into cache memory of user 2. Then if user 1 requests file A and user 2 requests file B, we don't have to send anything over the shared link. But if user 1 requests file B and user 2 requests file A, we have to send both files over the shared link. If we go through all the possible request scenarios, we see that the average load over the shared link becomes 1. But there is also another option in which we split each file into two equal sized parts. So we split file A into two equal sized parts A1 and A2 and file B into B1 and B2, and then put A1 and B1 in the cache memory of user 1 and A2 and B2 in the cache memory of user 2. Then if user 1 requests file A and user 2 requests file B, we can simply send A to X or B1. And user 1 can remove B1 using its cache contents and decode file A successfully. And similarly, user 2 can remove A2 and decode file B. Going over all different request possibilities, we see that the average load becomes half, and we see a gain of 2 here compared with the no coded scenario. This code word creation is why we are calling it coded caching. In general, it is shown that the coded caching enables a load reduction by a factor of T+1. T is the coded caching gain and is defined as a Km over N. K is the number of users, M is the memory size of each user, and N is the number of files. So this gain can be quite a large value, and it depends on the total cache size in the network. It's dependent on Km value. Interestingly, coded caching gain is additive with a spatial multiplexing gain of having multi-antenna communication. So if we have L transmitting antennas, the cumulative DOF, which means the number of users we can service with a single transmission, becomes T plus L. T is the coded caching gain and L is the multi-antenna gain. To see how this works, again, we consider a simple example, 3 users, 3 files A, B, C. The server has 2 antennas, and we split each file into 3 equal sized parts, and this is the cache placement. User 1 requests file A, user 2 requests file B, and user 3 requests file C. These are just random. This can be any combination of like 2 of them can request file A, another one file B. This works in any request pattern. So for this scenario, we create a code word for users 1 and 2, A2, X, or B1, and then we zero force or suppress it using beamformers at user 3. Because we have 2 antennas, we can suppress at 1 user. Similarly, we create a code word for users 1 and 3, A3, X, or B1, and zero force it at user 2. And another code word for users 2 and 3, B3, X, or C2, and zero force it at user 1. And with this single transmission, we can serve all the users simultaneously. So simply, we are creating code words for groups of size T+1, and we are mixing them using beamforming vectors. This is how we can get this cumulative gain. So coded caching works whenever we have some nearby users which have cache memories, and in fact, we have a memory pool that can be used. One application is rural connectivity scenario. These are just example applications. I'm going through 2 applications here. In rural connectivity scenario, we have a main base station, which can be a large tower base station or any other type of base station we have today. And some rural base stations and some rural areas in which in each of them there exist some user terminals or user equipments. By rural connectivity, we mean that these rural-based stations or rural UEs can be powered by unreliable harvested energy. This can be like energy from sun, from wind, or any other source of energy. When we have this unreliable energy source, we cannot guarantee a reliable connection. In some time we can have this excess energy, and some other time we can be low on energy. The idea is to use cache memories to store the energy whenever we have this excess energy. So this is general caching, not coded caching, but we can use this excess energy when available to fill up the cache memories. And in fact, we are storing energy in the form of data bits. However, here we have these clusters of users which are nearby each other, like this rural user equipments, or these rural base stations. From the point of view of this main base station, they can also form a memory pool. So coded caching be used to improve the performance in this scenario. And we are not only storing the energy in the form of data bits, but we are also using it in a very efficient way if we apply coded caching to this scenario. Of course, there are some issues that need to be solved. First, we need to tailor coded caching with unreliable energy availability. We need to tailor coded caching with different communication strategies. For example, these rural base stations can be simple relays or intelligent devices with coding, decoding ability. So we have to modify original coded caching schemes to work perfectly for this scenario. And then we can also use energy or data predictions to boost the performance. If we have this extra information, how we can use it. As another application, consider an immersive viewing scenario, which can be an industrial application, gaming, education. In this scenario, we have a hall. There's an area which there can be obstacles inside that area, and we have users which have this immersive viewing headsets, and this is a fully wireless scenario. And we want to provide each users with the data to be able to see the virtual interpretation of the location the user is standing at. Okay, in this scenario, because we need this very high quality, very high resolution video, and there might be some users nearby each other, we need very high data rates beyond what's available nowadays. And the first problem is that not only we need very high data rates, but we can have this bottleneck spaces where the data rate is low because we have limited number of these antenna arrays. Caching can help to smooth the rate curve, when the user pass closer to these antenna arrays, they can fill up their cache memories and then use this cache data to smooth the rate curve. However, in this scenario, we also have a memory pool because whatever the application be, industrial, gaming, or education, we have these nearby users. And we can use this memory pool via coded caching. Again, for this scenario, some issues need to be solved. When to update caches and what to put there, how to make coded caching more flexible for this dynamic environment. Coded caching is originally designed for static environments. And what software tricks can be used to improve the performance. Okay, we can split the video streams into static and dynamic parts and cache that static part, and that dynamic part should be delivered at the moment. Anyway, we cannot cache some dynamic data that's changing constantly. Okay, so after this few examples, let's say some research directions, what we are working on, and some other also research questions that are available for coded caching. One is the subpacketization bottleneck. Subpacketization is defined as the number of smaller parts each file should be split into. For coded caching, we need to split files into smaller parts. If you recall from the first slide, we split each file, files A and B, into 2 parts. So subpacketization was 2 in that example. Well-known coded caching schemes suffer from exponentially growing subpacketization. For example, the original coded caching scheme, the single antenna scheme, requires subpacketization of K choose T, and the original multi-antenna scheme requires subpacketization of K choose T multiplied by K minus T minus 1 choose L minus 1. Just to recall, K is the number of users, T is the coded caching gain, and L is the number of antenna. And it's obvious that both these grow exponentially with respect to the number of users. This makes coded caching infeasible, even for very small networks. Like if K becomes larger than 10, this can be a very large number, and it's impossible to split all the files into these very tiny pieces. In single antenna coded caching, it is not possible to reduce S considerably. Just for very specific parameters, it's possible. But for multi-antenna coded caching, interestingly, we can reduce the subpacketization without decreasing the degree of freedom. So, for example, in this paper, can refer to them later. I'm not going into technical details, but it is shown that if T and K are both divisible by L, this reduced subpacketization is possible. It still has some exponential form, but much smaller than the previous schemes. We have had this contribution recently that for networks in which L is larger than T, networks with large antenna arrays, we have shown that linear subpacketization of K times T plus L is achievable without degree of freedom loss. And this is some great contribution because we are going from exponential regime to the linear regime. In order to achieve this, we have used an algorithmic approach. This is just, for example, network, 6 users. We have this tabular representation or matrix representation, whatever. Columns represents user, and these rows represents file parts, and the C elements mean that these parts are cached at the respective user. And for this example, we have 6 users, T is equal to 2, and we have 3 antennas. And we have shown that these colored cells, they show the files that are sent, the file parts that are sent to the users in each transmission. And we have shown that with this kind of a scheme, that these 2 elements are shifted vertically, and these 3 are shifted horizontally. You can see that we are shifting these 3 blue cells horizontally and these 2 orange cells vertically. We have shown that with this kind of algorithmic approach, we can achieve this reduced subpacketization of K times T plus L. In another paper, we have shown that subpacketization can be further reduced by multiplication of 2 GCD terms. GCD is the greatest common divisor. And we have shown that under specific conditions, this is optimal, and we cannot go below this. Interestingly, it's possible to control subpacketization with this formula. We have shown that it's possible, and in order to do so, we set a spatial multiplexing gain to alpha. Alpha is smaller than L, and we are reducing degree of freedom, but we get some improved finite SNR performance. And again, I'm not going into technical details, but you can refer to the papers for more details. And then after subpacketization, there is this issue of multicast beamforming. Designing, coded caching requires, multi-antenna coded caching requires multicasting because we are selecting groups of users of size T plus 1 and then multicast coded data to these groups of users. And designing optimized multicast beamformers is generally complex. It's not just for coded caching, it's generally complex. And we need to find a solution for that. One option is to use zero force beamforming instead of optimized beamforming, but zero forcing results in poor performance, and especially at finite SNR, which is an important communication regime. We have proposed 2 possible solutions for this problem. One is to try zero forcing, but with reduced spatial multiplexing gain, the alpha parameter that are introduced in the previous slide. And another one is to try optimized beamformers with caching gain, but with reduced multicasting gain. These are proposed, these solutions are proposed in these 2 papers by Antti, my supervisor, and also another paper that we recently published. Just to give you an idea, this is a new scheme. These two curves, these intermediate curves, belong to the scheme that we have recently proposed. They have here, we see that this alpha parameter, if we reduce this alpha parameter, we get a gain at finite SNR. And also we see that this new scheme has a reduced multicasting gain. We remove all the multicasting and rely only on unicasting, but still we get the caching gain and this coded caching gain, in fact. And you see that we get a good gain compared to the no cache scenario, but we lose some performance compared with the original multi-antenna scheme that is very complex to implement. These figures are for these curves are for a very small network of six users, but this is what is achievable generally in the literature nowadays: 6 users, 8 users when we want to use optimized beamformers. But we have shown in this recent paper that we can go to networks of up to 100 users and like 25 antennas at the transmitter size. These large networks with large antenna arrays, with large in terms of coded caching, not generally. In massive MIMO, the numbers are much larger, but still, these are like acceptable numbers for current networks that we want to apply coded caching to. And we see that we get very good gain compared to the no caching scenario. Of course, there is some loss compared with the more complex solutions, but they are not scalable, and we have solved this scalability issue. Another issue with coded caching schemes is the strict cache placement phase. All the coded caching schemes are required strictly well-performed cache placement phase. The data in the user should be there's a clear pattern what we should have in the cache memory of users. So this makes coded caching not suitable for dynamic environments, for example, immersive viewing example, or unreliable connectivity environments such as the rural connectivity example. In order to solve this problem, we are now working on a new solution. This relies on probabilistic cache placement. We have an opportunistic approach to use cache contents in the form of coded caching whenever they are possible. This is a completely new scheme now we are working on. And we have shown that we can get good gain by increasing the caching probability. This kind of cache hit ratio, like in 50, if it's set to 50%, it means that 50% of the data request is available in the cache memories. And we use that available data in coded caching form with this new scheme. This can be combined by movement or energy prediction for improved performance. This is still in the development. In addition to these issues, there are also some other issues that need to be addressed. For example, some assumptions need to be relaxed for real-world implementation. Examples of these assumptions are file request probability, which is assumed to be the same at each user, and each user has this independent request probability. But in real-world scenario, they can be file request probability at each user may be different from other users, depend on the request probability of other users, or be predictable. We might have some information on what users are going to request, and this is not addressed still in the literature. There are some basic works, but not fully addressed. Also, there is this equal file size assumption in coded caching scenarios. This is clearly unrealistic. Most papers propose splitting files into equal sized parts, but this creates correlation, which is against other assumptions. So this also needs to be addressed. And moreover, coded caching needs to be studied under extreme conditions. For example, when the degree of freedom is much larger than the user count, this very large antenna arrays or massive MIMO, or when there are very few files, just 2-3 files in the library, or millions of files like YouTube or Netflix library that we want to cache. We should have a solution for this very small or very big file libraries. This is still an open problem. So as a summary, coded caching is an interesting tool, interesting option for increasing data rate in future networks. It works when a memory pool is available, for example, improved rural connectivity or improved immersive viewing, which are both important use cases of future networks. And we need to solve important issues for practical implementation. Subpacketization bottleneck, multicast beamformer design, this strict requirement for a placement phase, which can be solved by opportunistic coded caching. And also there are also other issues, relaxing unrealistic assumptions that are already there and addressing these extreme conditions. So coded caching is a great tool with notable research opportunity and many open problems to be solved. Thank you.